hello everybody. Now today we are going to discuss about a new class of materials which we refer to as gels. Now in particular we are going to discuss about supramolecular gels. So let us look at this process via diagram. So we have the supersaturated solution, and when we are cooling this supersaturated solution, it will lead to processes of nucleation and growth, and the process of nucleation and growth will give rise to particles which are being created or aggregates, and depending upon how these particles further grow, it can give rise to an amorphous precipitate. If it is a very controlled and a slow rate of evaporation of the solvent, it will lead to the formation of crystals, and then in between the amorphous phase and the crystalline state is, if we are cooling, there is an intermediate state which we refer to as the gel state, where essentially what happens, you have got these long fibrous assemblies, and these fibrous assemblies now get entangled with each other to form a 3D matrix, giving rise to the gel state. So the gel substance is viscoelastic, solid like material which is composed of an elastic cross-linked network and a solvent which is the major component. Almost greater than 90 to 95% is the solvent component here, and the rest is the gelating material which has got a elastic cross-linked structure. And the solvent is the major component, and when water is present, it is referred to as a hydrogel, because water is the major component which fills up the voids or the space which is created in this fibrous network. So when you have got these fibrillar structures are formed because of the process of self-assembly of the gelator molecules. So we are going to particularly focus on supramolecular gels. So in case of supramolecular gels, we have got the low molecular weight gelator substances. We have got the low molecular weight gelators, which we call LMWGs. And what happens in these substances, they essentially first interact in a supramolecular fashion via forming, say, the hydrogen bond assembly, and they form they glow like a chain. So there are strong interactions along which are mediating the formation of these chains, and they form this one ordered supramolecular assemblies, and then these fibril like structures can now laterally interact with the other fibrils to form the 2D network and eventually assemble into a 3D network. And during this process of cross-linking in other two directions, it can essentially get trapped in the matrix, and it can form this kind of fibril structures which are now forming this matrix, and now there are large amount of spaces where the solvents can get trapped, and essentially because the solvents now gets trapped, and this is because of the forces of addition between the solvent molecules and the low molecular weight gelators, and therefore this kind of freezes the motion of the solvent molecules. So now most of the solvent molecules get trapped in this three-dimensional matrix, which is created by the interlocking of these fibrillar structures, giving rise to a low molecular weight gelate substance. And these low molecular weight gelators, once they are formed, almost majority of it is the solvent, and some amount of it is the low molecular weight gelating substance. So, this low molecular weight gelators, they form the supramolecular association. They form the supramolecular association where they form these fibrous aggregates that get entangled during the process of aggregation and forming a matrix that traps the solvent via forces of adhesion between the solvent and the gelator molecule. So, this process, if it had ordered in a very ordered fashion, such that these fibrillar assemblies would have created a supramolecular periodic 3D array, it would have given rise to a crystal formation. So, sometimes it is also suggested that this gelation is a process of interrupted or arrested crystallization. These long lived supramolecular assemblies which are formed, they are stable and they exist in a solution, but essentially they are not able to crystallize further in an ordered fashion, because they tend to get trapped and tend to get locked into these highly disordered states in which we have this fibrillar structure like assembly. So, the gel network is actually a physically entangled network structure which has got these disordered regions along with the crystalline cross-linkers. So, it is a physical entanglement process. Okay. So, this is also a process of interrupted or arrested crystallization, which leads to the formation of these low molecular weight gelators. And by and large, these fibrillar networks are formed by say for example 1D arrangement by strong hydrogen bonds, or pi stacking, which mediates these self assembly processes. And then the other interactions which happen across the strand in the other two directions can give rise to the overall gel like substance. So, this leads to the formation of the low molecular weight gelators. Now, we also would like to see that gel formation depends on the origin, constitution and type of cross-linking that creates the 3D network and the medium they encompass. For example, the naturally occurring gelators are macromolecular in nature, and they are formed by physical cross-linking. For example, we have got gelatin and starch. When the gels are formed via strong chemical bonds, these cannot be redissolved and the processes are thermally irreversible. For example, polyamide and polyethylene. And now we can look at this classification on a more broader sense. So, we have the gels, we have got the source, natural or synthetic. Medium. So, one is the natural source, then one is the medium in which we get the gels. Here we have got 4 different classifications: organogels, hydrogels, ionogels and aerogels So, the organogels contain organic solvent, hydrogels contain water, the ionogels are formed from ionic liquids, and in aerogels gas is the fluid phase. Gas is the fluid phase. And we can also have constitution, that is, we can have low molecular weight gelators, we can have macromolecular gelators, and depending upon the extent of cross linking, we can have physical cross linking or chemical cross linking. These are covalent, as we mentioned, and these are fibers or particles held by non-covalent interactions. Short form is NCIs. Okay. And we have another classification here which is called metallogels in the medium, where the metal is present, in the sense that the metal is linked to the fiber components. Fiber is linked to the fiber, the metal here is linked to the fiber components to form gels. And a very straightforward procedure to make the gel is to dissolve it in a warm solution and then allow it to cool below T gel. A procedure to make gels is to dissolve the substance in a warm solution of a suitable solvent and then cool below T gel, which is also referred to as the temperature at which the gel forms, the temperature or the gelation temperature. And above this temperature, if you heat the substance, then it converts into the solution phase. The gel state is lost and it converts into the solution phase, and that is referred to as a gel to salt transition. But typically, if you want to prepare a gel, you dissolve it in a suitable solvent, warm it up and then cool it slowly below the gelation temperature, and this leads to the formation of a gel. And we also have got another classification of gel which is called thixotropic gel. Thixotropic gel, thixo. thixotropic gel. In this case, what happens is that you see that there is a gel substance, it undergoes a gel to sol transition when you stir the gel or disturb the gel state. So, you apply mechanical agitation to the gelatinous substances or the gel substance, it undergoes a conversion into the salt state, and when you either stir the gel or you shake the gel or you disturb the gel or you give it some mechanical activation, and the moment you withdraw the external stimuli, it again resets itself to the initial state and reverses back to the gel state when the stimuli is removed. For example, you can see paint. Paint you see is actually a gelatinous substance, but when you actually stir the paint solution, it starts flowing freely and it converts into a gel substance when it is at rest. So, paint is an example of a gel substance which becomes free flowing when you mechanically stir it or when you mechanically agitate it. So, it is free flowing like water, but again when you let it rest, it will come back to the gel state. So, these are some of the interesting things about gel, and initially all the research which was directed towards identification and discovery of gels was mostly serendipitous. That means most of the time people were trying to crystallize certain organic molecules or metal ligand complexes, and they observed the formation of this gel like substance. And there is a test which is referred to as the inversion test, which is performed to ascertain the formation of the gel. So, once the gel is formed, and it practically leads to the immobilization of the liquid. So, now you see you have this white solid which is dispersed in solvent, and it forms kind of a viscous mask. It is a viscoelastic material, and this is say the top of the container which is covered. Now, you actually put it upside down. So, this now becomes the top, and now what will happen, this gelatinous mass will essentially come and sticks, and it does not fall under gravity. So, this fall under gravity does not take place, telling you that this is a gelatinous state where there are strong forces of adhesion between the solvent molecules with the jelly like substance, and which actually sticks again with the glass surface, thereby preventing it to fall down freely under gravity, and it is a proof of the formation of a gel. So, this inversion test is interesting in characterizing the formation of gels. And let us now look at some of the important properties of gels. There are also gels that are very sensitive to temperature. For example, we have got the thermoresponsive gels. We have got the thermoresponsive gel. Let us take an example of a thermoresponsive gel. This is a bis urea compound. It forms a thermoresponsive gel at concentrations below 3 millimolar and are stable to 200 degrees centigrade. Is a stable to 100 degree centigrade. So, this is an example of a thermoresponsive gel. Now, we can look at the role of external stimuli such that you have got, for example, you have got a photo isomerizable group. You have got a photo isomerizable group which is present, and it is a part of the gelator molecule, and it undergoes a gel to solve phase transition in the presence of light, such that it converts the gelator substance to an isomer that does not gelate. So, let us look at this particular example. So, we can have this functionality. CH2PH CO2H in the presence of light, it can now convert into the from the cis to the trans geometry. So, the cis geometry does not form the gel, but the trans geometry forms the gel like state. So, this photochemical rearrangement takes place which leads to the formation of the trans geometry which has the gel state, but the cis geometry does not have one. So, we can actually go from the gel to the solid phase transition that is triggered by light, that can actually convert a gelator state to a non-gelator state and vice versa. So, we can take another example where we have got the diazo group, and the R is the cholesterol group. It is a large bulky group, the cholesterol group, and this is a photo responsive gel, and N-butanol gel of R, which is the cholesterol derivative. And what happens when you shine light 330 to 380 nanometer, it converts from the trans to the cis isomer, which does not form a gel state in solution. So, the gel property of this particular compound is in the trans geometry, but when you irradiate with 330 to 380 nanometer light, it loses the gel property when you pass light of different wavelengths. However, when you now pass light of 460 nanometer, it goes back to the gel state again. So, this is a reversible process where you can control the process of gelation. So, these two examples talk about the photo isomerizable group being important in gel formation. The next thing we would like to look at is the mechanism by which the gel formation is taking place. So, different models have been proposed, but we will look at some of the models which are responsible for aggregation of these low molecular weight gelator compounds to form the gel like assemblies. So, just like you have got protein aggregation which goes from the primary to the secondary to the tertiary structure, the formation of the gel network is also triggered by a hierarchical self assembly process, hierarchical self assembly process. It is a hierarchical self assembly process. So, for example, let us consider peptide based gels. So, we have got first of all these hydrogen bonds, So you can see that this form this kind of a 1D chain like structure around 5 angstrom in length. These can further aggregate extensively to form these kind of assemblies of 10 nanometer dimensions, and finally they can again grow into long fibrils which get entangled. So we can have these kind of fibril structures which will now get entangled to form this cross-linked network, and these are of 10 micrometer in terms of the dimensions, and these forms the gel or fibers. And the morphology can vary from aggregates to fibers to ribbons to sheets to micelles, vesicles, etc. So we have now learnt all these things in our previous lecture, so you can appreciate the formation of these structures giving rise to these gel like substances. And there are other ways also by which these can actually self assemble with each other. For example, this is one particular type of aggregation which I have talked about. The second one can be where you have got this CO NH moiety CO NH CO So what has been proposed is that you have now the polar parts, and you also have the non-polar parts. So the polar parts can form hydrogen bonds, and the non-polar parts so you can have these non-polar parts which actually now get entangled with each other, get cross-linked via this pi-pi stacking, and then the strong hydrogen bonds are mediated by these OHO hydrogen bonds. So you can have the stacking interactions and you can have the strong hydrogen bonds which can actually be formed, for example, in case of hydrogels, because the water can now solvate the polar regions, and the non-polar regions can now be present within the core, and so you have an organization by pi-pi stacking as well as OHO hydrogen bonds which can give rise to the gel like structure. And then there is another mode of association which is favored in case of anionic substances, where pH plays a very important role. So we can get gel to salt transition which can be controlled by the pH of the solution. For example, we can have these rod like fibers So we have these fibers which are present at high pH. Okay, which are present at high pH. And now when you add protons, you will see, let us represent these anionic species here. So this forms these stacks of anions. And now the protons will go and sit here and they will protonate these carboxylate groups and they will form these kind of microtubules actually, and eventually when you further lower the pH of the solution, that means increase the acidity of the medium, this will form microcrystals, which are the needles. Needle formation takes place. So what happens at the interface is the formation of these hydrogen bonds which takes place at the interface, because you added the proton source now, and they now lead to further aggregation from the fibers which are formed at high pH, and then they form these microtubes, and finally they will form the microcrystals. So you can control the morphology of the substance, and you can also control this this process of supramolecular assembly by tuning the pH of the solution, and will also change the property. It can go to the crystalline state via the microtubules starting from the micelle state. So these rod-like substances can now eventually convert into microneedles depending upon the pH of the solution. So these are some of the most important processes which takes place when we have gel-like substances, and so this gives rise to a very fascinating applications of gels. So with this we come to the conclusion of this lecture, and I hope you'll be able to appreciate the gel state, the liquid crystal state, and so on and so forth. Thank you.